Thank you, Ferdinand, for showing your face. Makes my life easier. The others don't hesitate to show your faces so that I can see if you frown or if you smile or if you're sleeping. Now, section 4.2, I'll go quite quickly over it. So I think it's Ivo, you were asking what is not really necessary. Well, this section 4.2, I had initially skipped it in the previous version of the slides, and then Monsieur Pandaven said that I was not allowed to skip it. So I included it. It's a theoretical result which is of importance. We won't really be using it, so if you, when you're studying, you don't reread this, you will not be really missing anything in the applications. But the Wald decomposition theorem says, it says basically that what we are doing makes sense and that mathematically everything is sound. So this result is essential for the theoretical understanding of stationary stochastic processes. And it says what? Well, it says that basically studying linear processes is good. More specifically, it says that any stationary process can be decomposed into one part of which will be deterministic, and another part which will be linear. So like this. So the whole decomposition says that any stationary stochastic process which has mean zero and finite variance will be represented in a unique way in terms of something which is a linear process with certain coefficients psi j's, this you recognize, plus a part which is deterministic. Now, what is deterministic? Well, it's something we've already encountered. So we say that a stationary process is deterministic or singular if it can be forecasted exactly from the infinite past. So we saw one example. It's this harmonic series that we constructed in example 2.26. This guy here, we saw that it could be reconstructed exactly from the previous two observations. So this process here is deterministic in the sense that you can, when you're projecting from xt minus 1 to xt and xt minus 2, what you obtain is exactly the value of xt. So purely deterministic process is something in which you have a variance which is zero when you're doing the projection. And the Wald decomposition theorem says, well, that you can always decompose in a unique way any stationary stochastic process in terms of something which is deterministic and something which is linear in the way that we like it. So studying linear processes is basically studying all stationary processes. And that's all I'm going to say about this. So let's go back to the course. So we have introduced the partial autocorrelation function. I will go back into it now. So again, the problem is the following. We want to forecast xn plus 1 from observations x1 to xn. We write this, so what we want is we want the xn plus 1 to be expressible in terms of something which is a projection of xn plus 1 onto the space here, plus some remainder term, which is the forecast error, and by assumption this guy will be uncorrelated with these guys, because this guy is equal to this guy minus this guy, and this guy is the optimum projection, and we have uncorrelation. Now, yeah, but Ferdinand, yes, but I'm also recording in my own system, so I don't know what Teams is doing. I'm not so confident in Teams. Maybe I should be. Now, What was I saying here? So this is, I'm just checking something here because I've written something and I'm now confused. So alpha 2, it means what? It means that x3, sorry, x, so alpha, yeah, okay, so I said something which is not entirely correct. It's this is not entirely correct. So what this is measuring here, it's alpha nn. This guy here is alpha nn, and in my writing, alpha nn is not the impact of adding information xn. It's the link. So this is at least right now, I think this is not very well phrased. So it's not really, I mean, yeah, I suppose I copied this from somewhere, but it's not really the importance of new information. It's more so alpha nn is the coefficient of x1 in the expansion. So you see here, we want to write xn plus 1. Where is he? Xn plus 1, we want to write it as something, so alpha nn is the coefficient of x1 in the expansion, not the coefficient of xn. It's the coefficient of x1. So alpha nn does not measure the impact of adding information xn. It measures the lingering importance of information x1 in the projection. So alpha nn measures the importance that remains of observation x1 on the quality of projection of xn plus 1. So what we saw in the case of an ARP process or AR1 process is that basically at step 1 x1 is important because x2 depends on x1, but at step 2 x1 is not important anymore. The impact of this observation will go away. So that's what's called the autocovariance, the partial autocorrelation function. And again, now we go back here. The partial autocorrelation function is given by alpha nn, which measures the contribution of observation x1 to the forecast at lag n plus 1. And well, basically you say that this contribution is 0 if this alpha nn is equal to 0. Now we have already worked out some particular cases. We have already seen that in the case of an ARP process, alpha nn is 0 if n is larger than p. And in the case of an MA1 process, we have seen that every new observation contributes to the recovering, and therefore alpha nn is not 0. So this is example 4.5 and 4.7. And if we look at the way this evolves in n, we get a function which is called the partial autocorrelation function. Now if you look it up on Wikipedia, that's not the definition of Wikipedia. I don't like the definition of Wikipedia. I don't understand the definition of Wikipedia. I mean, it works, it's computable, but I don't understand it. I don't find it intuitive. So I preferred this definition here. The partial autocorrelation function is the function alpha x of h, which says what? Well, alpha x of 0 is 1, like the autocorrelation function. Sorry. And alpha x of h is alpha h h, and alpha h h is the last entry in this vector here. And this last entry measures the importance of observation x1 in the prediction of xn plus 1. Now, I'll go quickly over this because you'll be doing it in the exercises anyway. You can compute this. We've already done it for the ARP. You can also do it for an MA1, and you will get this expression here. And here, well, you should be recognizing things which look like what was happening for the autocorrelation function of an autoregressive process. Something else is that If you have an invertible moving average process, then what you can see is that xt, it will be invertible with coefficients here which are never zero, and therefore xt is always correlated with all the xt minus h's, and therefore the PACF is never exactly zero. But you can show, and we won't be doing it, that this converges exponentially to zero. And the convergence is symmetric to the behavior of the ACF for autoregressive processes. And now let's look at a more applied example. So sunspots. So figure 4.1, we see the sunspots. Where is figure 4.1? Here. We see the sunspot numbers along with the ACF. And so here is the sunspots, that's the ACF. This is a simulated, so this ACF makes me believe that not a regressive process should be in order, because we have something which is not zero but which oscillates to zero. And then, I mean, this is perfectly arbitrary. I decided very, very arbitrarily that an AR2 process would be good. So I fixed my parameters like this. I mean, there's no justification. It's just me deciding to fix that like that. And then I look at the process, and I see that this looks more or less like, this here looks more or less like this, and this here looks more or less like this. Okay, so intuitively, it seems more or less not entirely incorrect to use an AR2 model to model this kind of data. But of course, we cannot be sure that some AR3 or 4 or something else wouldn't do a better job. And in order to convince ourselves that an AR2 model would be good, well, we can look at the partial autocorrelation function. Now, of course, you could imagine that computing this partial autocorrelation function is complicated, because it's, I remind you, it's given by this rather disgusting expression here. So it's the last entry of this vector here. But obviously, as you could expect, it's already encoded in R, and the function is super easy. It's just PACF. And once you do PACF, you get this. And here, what do we see? We see that the PACF is... That's the PACF of the sunspot series, and that's the PACF of the simulated series. And we see that they are not too far. So intuitively, with a lot of hand waving, it seems not unreasonable to use an AR2 or an AR3 model for the sunspot series. Now, this kind of thinking is the kind of thinking that you will have to be doing in the sequel. So that's how you do, actually, when you do real modeling, that's what you do. You look at the data, you take out whatever you see as seasonal, you take out the trend, you're left with the stationary series, and then you look at the ACF and PACF, and in terms of the behavior of the ACF and PACF, you guess a model, and then you check a few things, which I will show you next week. So it gets very, very easy. In practice, if you look at Wikipedia, maybe I should check my information. If you look at the partial autocorrelation function in Wikipedia, you should see a different definition. Autocorrelation function. Yeah, so in the partial autocorrelation function on Wikipedia, you see a different definition, which I don't really like, because it's not intuitive. So the partial autocorrelation function is given by the correlation, and that's where the name comes from, actually, why it's called a partial autocorrelation. It's the correlation between the projected, so it's the correlation between the difference between x h plus 1 as projection, so this guy here, and the difference between the corrected version of x1 and the projection of x1 onto the space. So you take, how to say this? So you take your xh, you look at the difference between xh and its prediction on the space, and you see the correlation between this guy and the projection of x1 onto the same space. And this gives you this very abstract and complicated definition, which has the advantage of being a bit more computable. And you can show, but we will not do it together, you can show that this is equivalent. So you can show that this guy here is in fact the same as the last entry in the vector, which is here. It's not really easy to show, and if you're interested, well, you can go and see in Neusser on page 62. He actually does the whole development. Yeah, I don't really feel like going into this. You can check it out on Wikipedia as well if you want. So this is the definition on Wikipedia. It's rather artificial, so I really prefer the previous one. Okay, now if I summarize all this, we have this nice table which is, well, super important for the modeling process. So it's called Box-Jenkins methodology. When you have an ARP model, you know that the autocorrelation function declines exponentially, either decreasing or oscillating to 0, and the partial autocorrelation function is something, 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 then drops to 0. And when you have a moving average model, purely moving average, the PACF declines monotonistically, either oscillating or directly. The PACF declines exponentially, either monotonically or oscillatingly to 0, and the autocorrelation function goes something, 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 and then drops to 0. And well, basically, simply by looking at this guy and this guy, you can already give yourself quite a good intuition as to what kind of model you will need to use for your data. Now, you might wonder what's happening when you have RMAP PQ, when you have a mixture. Well, we will be doing this in chapter 6, so next week. So far, so good? Okay. Now, I lied. I can't go over this section. We have to do it. You have to know about the innovations algorithm. So I'll go quickly. Yeah, it's something we have to do, so let's do it. So in principle, alpha and n can be obtained from these equations here. The problem is that as n grows, well, you're inverting a sequence of increasingly large matrices. Gamma n is n times n, so if you're at 1000, you have 1000 times 1000. You have 1000 times 1000 square matrix that you have to invert. That's pretty disgusting to do. And for any n, you have a new matrix, so you have a new solution, so everything has to be done again. So this is numerically costly, and every time you change the n, you have to recalculate anything, and that's everything, and that's quite annoying. It's less relevant now in 2020, but it was very relevant 20 or so years ago, because that was very complicated to do. And because of this, well, humankind is very ingenious, so they invented a way of computing these terms recursively, despite the fact that you had to recalculate each time. And this gave rise to something which is called the innovations algorithm. And this innovations algorithm is at the heart of what, well, for example, the ARIMA function that we were talking about with Orphée. This ARIMA function uses Gaussian likelihood estimation, and this Gaussian likelihood estimation does all the estimations thanks to this innovations algorithm. Well, to a version of this innovations algorithm. So let's quickly explain how this works. We have a process about which the only assumption we make is that it has mean 0. We don't assume stationarity. It's not necessary for the algorithm to work. Now, let's look at something that I call Kij, which is the covariance function, covariance kernel, So here it's just the scalar product of xi with xj, and we suppose that these guys have a finite variance, otherwise nothing that we're doing makes sense. Now we project, oh that's a typo, we project xn plus 1 onto the span of x1 to xn, so no independent part because you have taken zero mean. So we project xn plus 1 onto the span here. We call this x hat n plus 1. But instead of doing this like this, we do it on an orthogonalized version of the basis. So we set x hat 1 equals to 0. We notice that the span of the vectors x1 to xn is the same as the span of the vectors which have been recentered, like this. So maybe a little drawing. It's called Gram-Schmidt. So I know the mathematicians among you have heard about it. Engineers probably will also have heard about it. The idea is that if you have two vectors which are not orthogonal, you can always make them orthogonal simply by you choose one of them as your basis, this one, and then you project orthogonally this one on the complement, so on the orthogonal projection of the basis. And now you have orthogonalized your vectors v1 and v2. And then the second step is that you can always normalize. So if you divide by the norm, like this, you can always normalize to have norm 1 vectors. So any vectors in a vector space can always be, so any system of independent vectors in a vector space can always be orthogonalized. How do you do that? Well, simply you just take the projections onto the orthogonal complements of the vectors, and you do this recursively, and then they can always be normalized. And the process by which you do this is simply called, well, it's called Gram-Schmidt orthogonalization. I'm guessing most of you must have heard about this. At least a fairly nice saying yes. The others I can't see your faces, so I'm guessing you're all nodding enthusiastically. And this gives us what? Well, it gives us a way of rewriting the optimal projection of x1 to xn. Sorry, the optimal projection of xn plus 1 on the space of xn of x1 to xn, but now with different coefficients. The coefficients are not the same because you're looking in the basis of orthogonal vectors made up by your system. So here, for example, in my drawing, if I had a point here, let's say that guy would be a certain number of times this one plus a certain number of times this one, but it will also be a certain number of times this one plus a certain number of times this one. It's the same guy, but it has a different representation in this basis than it would have in this basis. And that's what's being said here. We keep the same projection, but we have different coefficients. Now, there is no difference in this guy, but the basis is much nicer because by making them orthogonal, we have very nice people because they're all orthogonal. So whenever you're taking products of these guys, a lot of things will cancel out and will make the system much simpler. So it becomes much easier to determine these theta nj's than it is to determine the alpha n's. But once you have the theta nj's, you have the alpha nj's as well, because they are there's a bijection between the two. So far, so good. So the idea behind the innovations algorithm is very, I mean, if you know a bit about this kind of, so if you've played around with vector spaces, it's not a surprise. If you're looking at a way of writing a vector in a vector space, it's much nicer if the basis is orthogonal than if the basis is not orthogonal. And then when you just work out these guys, that's going to be easier, and then from here you work out the alpha and j's. And this gives us the algorithm here, which, well, it's just a matter of writing it out. Assume you have zero mean, covariance here. Suppose that this covariance is non-singular. That's important. We defined a new case. We had these new cases we had defined before, so these are just the mean square error of the projection. And then the coefficients for this guy can be, so these coefficients here, the theta j's, can be obtained recursively. So the alpha j's cannot. That's too ugly. Each time you mix up, you have things that it becomes too ugly. But the theta j's can be computed recursively. Nu 0 is just k of 1, 1, and then you get this system of equations here. I'm not going to go into the details because I will be giving the proof. So this just comes from computations. This follows from direct computations. You see the idea? Nobody's complaining, so it means that either you're all asleep or you all see. Now, how do you do this? Well, it's just the definitions. X hat 1 is 0, so nu 0 is just expectation of x1 squared. So that's just the variance k11. So that's immediate. And now theta n minus k, well, you just do it recursively. You see that this coefficient is given by this expression here. Work out the expression, and Bob's your uncle. So it's just a computation. You probably don't know the expression Bob's your uncle. That's...
You already used it.
Sorry?
You already used it in the team.
Yeah, it's... don't use it in public. It's really... C'est ringard. I left, so I was brought up when I was very small in an English-speaking country, and I left this English-speaking country when I was 6, and I still have a lot of my expressions are the expressions of a 6-year-old, which is quite pathetic. But so don't use my expressions unless you want to lose your friends. So there we get the theta n minus k's, and then for the new n's, well, again, just write out what it is. Nu n is this variance here. It's by definition this thing, and then you do all these computations, and you get this expression here. I expect you to be able to do this. I mean, I can't ask you about this because it's not a question that I can ask you in an exam. It doesn't make sense. I can't ask you to copy this kind of thing, but I expect you to be able to do it. So please earnestly try to do these computations and check that you actually understand what's written. It shouldn't be too long. It's I mean, it follows from the definitions, and this gives us an algorithm, because you start at level 0, you compute nu 0. Then from this nu 0 you get theta 1 1, from which you get nu 1. From this nu 1 you get theta 2 2, from which you get theta 2 1, from which you get nu 2, and so on. And you have a way of computing these guys, and that can be implemented in the computer, and then it can be implemented quite easy, because none of this is expensive. None of this is expensive. It's just sums of things that you compute. So it's very, very easy. So it's not like here. Here you're inverting disgusting matrices. Inverting a matrix is n to the power cubed operations. So if n is 1,000, you have 1,000 cubed. This is disgusting. Here it's just sums. So it's linear in the number of terms. So it's going to go very, very fast. That's what R does, actually. It's this algorithm here, which is the basis of ARIMA algorithm. And you can try it out on the moving average of order 1. The covariances of this form, and then the innovation algorithm, again, that's computations that you need to do. I'm not going to do them for you. There's no point in me working out these computations, but you work out these computations by yourself, and you see that you get all the terms here. And this gives us the expression here. Moving forward, if you have an RMAP process, you can also do, is this, yeah, this I don't ask, I mean this would take you hours, so don't try. I mean, you can, of course, but I guess you also have a life on the side, so you can do it in general for an RMAP process, but it would take you hours, so I'm guessing this would be very, very long. I think. Can't really remember that. I think. So when I'm saying it's not detailed here, it's probably because I'm being very, very lazy. And I myself would not have the courage to do it. So I'm not saying I wouldn't ask you this at the exam, but I would try it first, and I would ask you a version of this which would be doable. So if you want to do it beforehand, you can, but it will take you a long time. If I ask you something like this at the exam, it will mean that I will have decomposed the question into small steps that are doable in a finite amount of time. Okay, so far? Okay, so now we can move on. I seem to be moving quite fast. Is it not? It's okay. So I'm leaving you quite a lot of work. I will do, maybe we'll just do one more. So we do 3/4 of an hour more. We stop at 5, and then I'll stay here for questions if there's any questions, or you can just go back to your lives. Because I am skipping a few things, so there's quite a lot of work for you to do on the side, so I don't want to overburden you either. Okay, so chapter 5 is, we're back in a nicer zone. Things are a bit nicer now, because we have done all the job, we have done all the work for giving ourselves the definitions, we have the ACF, we have the PACF, and now, well, basically we want to understand. So you saw this function ARIMA in R. We want to understand what he's doing, and chapter 5 and chapter 6 explain what ARIMA is doing, and explain how, like, they explain basically the important part for you. So I mean, the theory is nice, but in practice you have x1 to xn, and you want to extract information from this x1 to xn. So in the previous chapters, 1 to 4, we have seen in which way the mean and the autocovariance functions of a stationary stochastic process characterize its dynamic properties. Everything is characterized in these gamma h. At least, of course, at least if we restrict ourselves to the first two moments. If we're looking at higher order moments, then we will need higher moments for the process, but that's not something we're going to be dealing with here. So in particular, we have investigated how the autocovariance function is related to the coefficients of the corresponding ARMA process, and that means that estimating the ACF is not only interesting for its own sake, but it's also interesting for the specification and identification of ARMA models. So what we want now is we want reliable, consistent estimators for these quantities here. Also, we will want to test things. We want to say, well, is my noise process stationary? Well, I want to test that. I have a statistical test which will give me a p-value, which will give me some trust in the fact that I have been doing a good job or not. So, as usual, small sample distributions are disgusting. They are complicated mixtures of complicated distributions, and what saves statistics is asymptotics. So you've already done this with Mr. Verdebout, you've already done this with I don't know who your other professors are. David Kranestoffer, maybe you have him. David van der Ven, all these guys. Well, they're all doing asymptotics. So small n properties are disgusting. Large n properties are basically always Gaussian or chi-squared, because everything becomes Gaussian or chi-squared as n grows. Now, the problem is that all these classical theorems do not apply here, because so standard sampling theory is not appropriate. Because why? Well, because the xt's are not independent. They come from a given stochastic process. Don't forget the situation. You have a stochastic process, and your xt's are sampled from this process. So they are systematically related to each other. So we have to adapt the classical theory. Now, while I was preparing this course last year, I hesitated for a long time at giving proofs of all these asymptotic properties, because they're actually quite pretty, but it's really hard. I mean, it's hours and hours and hours of computations. So in the end, I decided not to. So if you feel frustrated at not seeing the proofs of these results, well, I'll be glad to point you to the. I think I actually do it. I always point you to the appropriate pages, so you can read it up for yourself. So if you're so inclined, it's actually worth doing. It's actually quite interesting, but it's a huge amount of work. Even for the simplest theorems, it's a huge amount of work. So I'm going to be now in this chapter and the next one. I'll be basically cheating, and I won't be giving you the proofs of the claims. So let's start with the sample mean. The sample mean is of this form, and there's an asymptotic Gaussianity result, which is here. It says that if your process is stationary, if it's linear, depending on IID, so it's not white noise anymore, it's IID, so I'm making a stronger assumption, and if your coefficients are absolutely summable, and the absolute sum is not, and the sum is not zero, then your sample mean is asymptotically normal with mean mu, of course, and with variance 1 over n times this thing here. So asymptotically, for example, if you have AR process, we can compute this. If you have a moving average process, you can compute this. Asymptotically, you know the approximate distribution of x bar n. You know that x bar n is approximately going to be distributed according to a normal with mean mu and variance sigma squared over n times that sum here. And well, that's just beautiful. You must admit that this is just absolutely beautiful. It's a stunning result. The traditional result for a multivariate Gaussian would be without this guy, and because of the dependence of the process, we have to the variance becomes larger, and becomes larger by this amount here. Let's have a look at a few examples. Let's suppose that xt is already a Gaussian process. Well, then you can compute this exactly, and you will get this this result here. This is an exact result and not an asymptotic distribution. We've already done this. I forget where, but we've already done this computation. The asymptotic variance here, where it depends on the sum of all the covariances, and this is called the long-run variance of xt. And well, this guy is the correct correction for your asymptotic results. So it's not going to be the sigma squared; it's going to be this guy here, which will be useful for the prediction and for the testing and for the whole theory. Okay. Now for the autocovariance and the autocorrelation, similar things happen, but it starts with again, I can get I'm an excitable guy, and this gets me very, very excited, because we have seen that what's super important is that these covariance matrices here be invertible. If they are invertible, then everything works well. If they're not invertible, then things get messy. Now, in practice, what you're going to do is you're going to be working with estimated covariance matrix, and the estimated covariance matrix is the same thing here, but you put little hats over everybody, and you replace this guy by the estimated variance, this guy by the estimated covariance at lag 1, and this guy by the estimated covariance at lag 2, and so on. So you get an estimated matrix. And now you may be thinking, well, that's a very complicated random variable. For every x1 to xn, you get a different matrix here, and so you have a random matrix, and this random matrix will have certain properties. And you might be thinking, well then the whole theory is basically condemned, because we will not have invertibility, and if you don't have invertibility, nothing is going to work. Well, surprisingly, at least for me, you always have invertibility. Sample covariance matrices are always invertible. Now just let this sink in a bit. We have a random matrix here whose determinant will always be different from 0. Always, whatever the sample. If you're looking at a stochastic process which is stationary, this matrix here is always, almost surely, for all n, it's invertible. And the proof is, well, the proof is super simple. You see it's here. So how do we do this? Well, let's imagine that n is fixed. Let's imagine that n is fixed. So gamma hat of h, is this thing here. And gamma hat of h is only defined up to h is equal to n. If, well, h is equal to n minus 1. At h, n plus 1 and so on, it's not defined. So the first thing we do is we extend the definition of gamma h to the entire set of integers by fixing this like this. We say that gamma hat of h is 0 for any h larger than n. And now the proof is in 2 steps. Step 1, we show that this matrix is always definite positive definite, well, non-negative definite. That's step 1. Step 2, well, we have theorem 1.38, which said that if you have a function which is which goes to 0 as h grows, and which is such that all these matrices here are non-negative definite, then this function is the autocovariance function of a stationary process. Okay, but then step 3, because gamma hat of h is 0 for all h larger than n, we also know by proposition 3.38 that this is in fact the autocovariance of a moving average process of order n minus 1. But if it is the moving average, if it is the autocovariance of a moving average of order n minus 1, then lemma 4.1 applies, and we know that this thing here is necessarily positive. So for any x1 to xn, this matrix here, where is it? This matrix here will be non-negative definite because of the argument I'm going to give you in a second, and therefore the corresponding covariance function that you define is a covariance function of a certain moving average process, and therefore it's invertible. Now, how do you do this non-negative definite? Well, you cheat. You rewrite this matrix here. So this matrix here, it has a very specific form. It's sums of xt minus xn's like this. So what we do, maybe I should detail it here. So theorem 5.2. So gamma hat k is the matrix gamma hat of 0, gamma hat of 1. I'll do it for k is equal to 2. 3. So that you see it correctly. So this is what? This is 1 over n times what? Well, here I have the sum of the xt minus xn, sorry, the xt minus x bar n, so x bar 3 squared, so t going from 1 to 3. Here I have the sum for t going from 1 to 2 of this guy. And I'm going to run out of space, so like this. And then I have this guy here. So I'm doing nothing here, I'm just writing out explicitly what this guy is. So then this I can simply copy, put it here, put it here, and this guy goes here, and I will get the same guy here, like that, and this guy here. So I'm just writing out the different terms explicitly. Like that. So I have a nice matrix. Of course it's 1/3. Like that. I'm a happy camper now. And what I'm saying that this is the same thing as, so let's make this smaller. This is the same thing as, so I take x1 minus x1 x3 bar. I take x2 minus x3 bar. And I take x3 minus x3 bar. And then I take 0. I'll do this slowly. So K is this correct? Yes, I think it is. I think I'm happy here. So I'll call this T3 prime, and if I do this guy multiplied by the same guy in column, what do I get? Well, I get this is a 3 by 1, 2, 3, 4, 5. So this is a 3 by 5 matrix. And if I do tk prime, well, t3 prime times t3, what do I have? Well, and line, so this will then be 3 by 5 multiplied by a 5 by 3, which gives me a 3 by 3 matrix. Term 1, 1, I have x1 minus x3 bar squared plus x2 minus 3 bar squared plus x3 minus 3 bar squared gives me this guy. Term 1, 2, I have this guy times this guy. Is that correct? So I'll have x1 minus x3 bar times x2 minus x3 bar plus x2 minus x3 bar times x3 minus x3 bar, and so this will give me this term, and so on. So by writing this out explicitly, I see that this multiplied by the same thing in column will give me exactly these terms here. But what's the advantage of this? Well, it means that we have rewritten our covariance matrix as what? Well, as a product of two. Well, it's as a square. In fact, we have written it as this matrix times the same matrix in column. Yeah, but that's good, because then if we pre-multiply to the left and to the right here, we can I can detail that. Then what happens if we have a prime times gamma k hat a? This is just a prime times tk prime times tk, I put a hat, times ak. but that's the same thing as TKA primes times TKA with a hat, and that's exactly the squared norm of TK hat A, which is necessarily positive. Therefore, this trick here of rewriting the covariance, so we are explicitly using the fact that the covariance is a sum of terms which are moving. So it's a sum. It's a sum of terms here, and then by using this exact expression of the sum of terms, we can rewrite our covariance in this form. And with this rewriting, we get the fact that we have a non-negative definite matrix, whatever the values of x1 to xn. Okay? So with this crazy result, we get a very important formula, which I will ask you to manipulate. So we don't do the proof; it's just too complicated, at least for this course here. Which says that if you have a linear process of this form, if the coefficients are absolutely summable, and this is an additional condition of convergence to zero, so we ask more than that. We ask actually quite a lot more than this. We need that they go to zero very, very well, sufficiently fast for this to be finite. Then we have the very beautiful result, which is here, which says that the vector of autocorrelations, this guy here, is asymptotically normal with mean the autocorrelations, so it's consistent, and with covariance given by something called Bartlett's formula, which you will be manipulating in the exercises. So it's something like this. It's quite ugly, but it's computable. Okay. So when can you apply this convergence result? Well, you can apply it. That's not well written. I'm very, very sorry. There's something strange here. Yeah, that's not well written. What I should have written is this. Like this. Yeah, okay, I'll just so what I should have written was this. Like that. That's better. So what it tells us that the vector of autocovariances is approximately normal with mean the vector of theoretical covariances, and with variance 1 over n times this matrix W given by Bartlett's formula. And you can reasonably use this approximation here. So this approximation here, you can reasonably use it when n is larger than 50 and the order of the correlation coefficients are less than n over 4, and that's just folklore. I mean, I don't think there is a proof yet of that kind of assumption. Now this allows us to understand one of the things that R does automatically. So when you use R's autocorrelation function, you immediately obtain these blue lines, and these blue lines report the confidence intervals for the estimates of your coefficients. So if you're estimating your coefficients, you have you can associate to each estimate confidence interval at lag. Let's say at lag 1 we look at this order here at lag 1, and the associated confidence interval comes from the normality assumption. So let's look here. The most important application of theorem 5.3 is related to the case of the white noise sequence. Then your Wij's are given by this, just ones or zeros, it's just the identity, so W is the identity matrix. And that means that the asymptotic distribution of your correlations is asymptotically standard normal, and therefore we can have the usual confidence interval, which is just 1 plus 1.96 divided by square root of n. So this is what you see here. So how do we interpret this? Well, we interpret it in the fact of saying that any autocorrelation value which is less than, which is inside these blue lines, can be is negligible and can be disregarded. So any autocorrelation value which is under these blue lines is in fact can be approximated by 0 and with certain confidence. Similarly, if you have moving average, then you can compute your confidence interval with the same theorem. Here the Wi's are not the identity, but they are this thing here, and this you will be doing in the exercises. And this gives us another confidence interval which is of this form. All this is already pre-implemented in R, so you don't have to worry about computing them explicitly. It's already done in the R algorithm. And same thing for the R1 process. You can compute the corresponding Bartlett's formula, and this is again something you'll be doing in the exercises, and you get these confidence intervals here. So far, okay? Okay. So the same thing, so I'll go fast now because it's always the same idea. The same thing can be done for the partial autocorrelation function, which is also quite important. So by definition, at least with our definition, the partial autocorrelation function is the last element of this vector here. But now we know how to estimate this guy and this guy, we can therefore estimate this guy. And then you just have to be very, very, very courageous to combine the previous theorems in order to get covariance, to get limiting distribution of this guy. And one can show that, again, because this guy is asymptotically, so this guy is always invertible, this guy is asymptotically consistent, well then this guy will also be consistent and asymptotically normal, and we have this result here, which gives us which allows us to obtain the confidence intervals for the partial autocorrelation function. So this gives us these blue lines here that we see in the partial autocorrelation plots associated to our process. And I think, yeah, I think you've gone fast enough over all this, so we'll stop here for today. Next week we'll cover chapter 6 and some corrections of exercise session, well, 4 at least, and if there's any questions about exercise session 3. And you already now have all the material you need to cover exercise session 5, and next week we will cover exercise session 5 and whatever, so the week after we'll cover whatever is in the further topics. I will probably completely rewrite this chapter, so I'm not happy with what's in here for the moment, so I will send you a new version of this chapter 7 as soon as it's written. So next week we will do this chapter. It will go very fast, at least this first part, this part here. this part here will go very fast, and that we'll probably keep it for the week after. So that's what we'll do. Okay? If there's any questions on the material, I'm here. So otherwise, just have a good week.